Hello everyone, welcome to the 31st episode of this series. In this video, we'll learn how to find eigenbases for a matrix A. So in the last episode, we were introduced to the notion of an eigenbasis, and we saw that eigenbases play well with matrix multiplication. So as I said, in this episode, we'll learn how to find an eigenbasis. So we'll start with the algorithm directly. So let's say we're given an n by n matrix A. The first thing we do is we find all the eigenvalues of A. And to do that, we compute its characteristic polynomial and then find all the roots. Then for each eigenvalue lambda, we find a basis of the lambda eigenspace. That is, we find a basis for the kernel of the matrix A minus lambda I. We do it for each lambda, and then we get a collection of these bases for the kernel of these matrices. So we take all of these vectors from all of these bases and we put them together in a single set. Now, if there are exactly n vectors in that set has to be an eigenbasis. And if there are fewer than n vectors, then no eigenbasis exists for the matrix A. This algorithm constructs linearly independent set, and this is what actually makes this work. So let's look at an exercise. We're given a 2 by 2 matrix B. So we either have to find an eigenbasis using this algorithm or get to the conclusion that it does not exist. So the first step, as I said earlier, is to find the eigenvalues. And in this problem, I am going to assume that you guys remember how to do all of these things. So I'm going to talk about the key steps, but I'm not going to go over the details. If you are stuck, please revisit the older lectures. So the characteristic polynomial can be computed to be x squared minus 4x plus 2. And when you factor it using the quadratic formula, you get that the eigenvalues are 2 plus square root of 2 and 2 minus square root of 2. So once we have the eigenvalues, we want to find the eigen space for each of the eigenvalues. So the eigenspace for the eigenvalue 2 plus square root of 2 is the kernel of this matrix B minus identity times 2 plus square root of 2. And similarly, there is an eigenspace defined for 2 minus square root of 2. So we know exactly how to compute a basis for the kernel of a matrix. We had an explicit algorithm in episode 28. So we just use that. And feel free to check the computation. But when you do this, you will get a basis for each of these eigen spaces. And the bases are going to look like this. Both of these bases will have exactly one vector each. So when you put the vectors in these two bases together in a single set, we get the collection of two vectors. Now, this has two elements, and the fact following the algorithm said that they are linearly independent. Therefore, this has to be an eigenbasis. So we saw how to compute an eigenbasis for a matrix A. But what if we want something weaker than that? What if we just want an answer to the question, are there enough vectors to actually form an eigenbasis? So if that's what we want, the following fact is going to be very helpful. So any matrix A has an eigenbasis if and only if the width of A is the sum of dimensions of all the eigenspaces. So you compute all the eigenvalues. For each eigenvalue, you compute the eigenspace. And you take the dimension of each of these eigenspaces, and if the sum of that is exactly equal to the width of the matrix, then that matrix is going to have an eigenbasis. So let's look at an exercise. We're given a 3 by 3 matrix A, and we're also given the information that A has two eigenvalues, 1 and 7. And we want to show that A has an eigenbasis, and we want to do so without finding the eigenbasis itself. So we're going to start with the matrices A minus lambda ID. So, we take our two eigenvalues and we compute the A minus lambda IDs corresponding to them. So we get these two matrices. Now let's focus on the first matrix, that is A minus 1 ID. Now, because all the columns of A minus 1 ID are multiples of each other, as you can see, the first and the last column are the same, and the middle column is 2 times either of the columns. We get that the rank of this matrix is 1, which by the rank nullity theorem gives us that the dimension of the one eigenspace, which can be calculated as the width minus the rank, is actually just 3 minus 1, which is just 2. So the dimension of the one eigenspace is 2. Now, in a similar manner, we can investigate the matrix A minus 7 ID. Now, if you pay attention, this matrix cannot have rank 0 because it's not the 0 matrix. It cannot have rank 1 because the columns are not multiples of each other. And it cannot have rank 3 because if you compute its determinant, it's actually 0. So by elimination, that tells us that the rank of A minus 7 ID has to be 2. And that, by the rank nullity theorem, gives us that the dimension of the 7 eigenspace is actually 1. So what we get is that the sum of the dimension of the eigenspaces is 1 plus 2, which is 3, which is exactly the width of A. And as a result, A has an eigenbasis. Now, here's a useful trick. If lambda is an eigenvalue of A, then that means that there is at least one lambda eigenvector. So if there's at least one lambda eigenvector, then the lambda eigenspace is dimension at least 1, and therefore a basis for the lambda eigenspace has at least one vector. So if we have a characteristic polynomial that gives us distinct roots. So remember that because the matrices are of size n by n, the characteristic polynomial will be of degree n. So if it has n distinct roots, we actually get this very powerful result that if it has n many distinct roots, that is eigenvalues, it must have an eigenbasis. And this is just a simplification in this special case of the observation that we saw a moment ago that related the width of the matrix to the sum of the dimensions of the eigenspaces. But do note that if the n by n matrix has fewer than n distinct eigenvalues, then it may have an eigenbasis or it may not. We'll need to use the algorithm or some other methods to actually find out. Okay, so let's look at an exercise where we determine whether a given matrix has an eigenbasis. So we're given this 3 by 3 matrix. We're going to start with the characteristic polynomial of this matrix. So it's, we just multiply the identity with x, subtract c, and then take the determinant. And we get x cubed minus 2x squared minus 2. Now, every term has an x multiplied to it, so we can at least factor the x out. So we get x times x squared minus 2x minus 2, which gives us that one of the roots is x equal to 0. Now, for the other roots, we just need to factor this quadratic polynomial, and we can do that using the quadratic formula, and that gives us that x is 1 plus square root of 3 and 1 minus square root of 3. So the three eigenvalues are 0, 1 plus square root of 3, and 1 minus square root of 3. So since all the eigenvalues are distinct, we conclude that C has an eigenbasis. So I want to end this episode with a very important result, and that's a bound on the dimension of an eigenspace. So if lambda is an eigenvalue for matrix A, then we've already discussed that because there will be at least one eigenvector, the dimension of the lambda eigenspace is going to be at least 1. But on the other side, we have an upper bound as well, and that is that the dimension of the eigenspace corresponding to lambda is going to be at most the number of times x minus lambda appears in the factorization of the characteristic polynomial. So in other words, if lambda is a root of the characteristic polynomial PAX with multiplicity m, that is, it appears m times, then the dimension of the eigenspace is going to be between 1 and m. So, here's an important thing to remember, that there are two notions of multiplicities for eigenvalues. In other words, two different ways to count an eigenvalue. One of them is called the geometric multiplicity, and the other is called the algebraic multiplicity. So, geometric multiplicity of the eigenvalue lambda is just the dimension of the lambda eigenspace. And the algebraic multiplicity of the eigenvalue lambda is just the number of times x minus lambda appears in the characteristic polynomial, or in the factorization of the characteristic polynomial. So with this, I would like to end this episode. Hopefully things were clear. I will see you guys soon. Till then, happy learning.